Hello everyone, my name is Vladyslav Sarnatskyi. I'm a PhD student at National Technical University of Ukraine, Kyiv Polytechnical University. During this presentation, I want to share our results on efficient single-core execution of agent-based epidemiological models with contact tracing transmission. Agent-based models in epidemiology are getting more and more popular last 3 years. These models, as opposed to compartmental ones, consider target population as a set of distinct agents. Each agent is a separate entity, with its own set of parameters, its own schedule of activities, etc. Agents can interact, thus contributing to the spread of a model disease. To account these interactions, a trivial algorithm would need to iterate through all pairs of agents, resulting in its quadratic complexity, which is a problem for medium and large models, as for example, a model with 1 million agents, which is far from being large, requires half of the trillion interactions to account. Main aims of this research are to formulate a general mathematical background for agent-based epidemiological models, to explore the ways to optimize complexity of simulation algorithms, and compare the performance to previously made models and approaches. To better understand the domain we are building a mathematical model for, we performed a literature review on existing tools and approaches of agent-based epidemiological models. We separated them into 3 distinct categories: programming language models and libraries, which include tools that extend certain programming languages by offering a toolkit for defining and running epidemiological models. This category includes such tools as Swarm and Escape. Second category is general-purpose modeling environments. This category includes software which is designed to be used for general modeling tasks like NetLogo and Repast. Often these tools offer interface to a modeling language which is used to define these models. Even though they can be flexible and suitable for usage in the field of agent-based epidemiological models, their performance is questionable. Last category is specialized software for epidemiological modeling. It contains standalone software for defining agent-based epidemiological models, like for example Phred model. As each instance of agent-based epidemiological model can be assigned to this category, we only select those which offer some kind of flexibility in model parameterization. This kind of software provides the best performance, but often lacking the flexibility of general-purpose modeling tools. Our mathematical model describes 2 sets of entities, agents and places. By place we mean a geographical location where agents can interact. For example, workplace, school, shopping mall, etc. As epidemiological models are dynamic in time, we have a set of simulation steps, T, and time steps, H. Each simulation step consists of several time steps. The only difference between them is that agents can change their infection state only at the end of simulation step. Simulation steps can be thought of as days, time steps hours. Agents can move around by following their schedule function phi. It tells at which place agent is situated at given simulation and time step. Infection model consists of a set of infection states. For example, susceptible, infectious, and recovered, to mimic classical SIR model. Each agent has its infection state, which can change each simulation step. This relationship is dictated by infection state function xi. Infection state can change as the result of 2 processes. First one, the process occurring inside each agent's organism. For example, infected agent can recover by itself. To model this process, infection is specified by infection progress function phi_p. This function for each agent returns the probability distribution of infection states at next simulation step. For example, for infected agent, this function can return that its state will be changed to susceptible with probability of 0, to recovered with probability of 10%, and left as infected with probability of 90%. Secondly, infection states can change as the result of interactions between agents. Mostly, this means that agents can infect each other. To capture this behavior, infection transmission function phi_t is defined. It tells the probability distribution of recipient's agent's infection states at next simulation step after a contact with donor agent. Given these definitions, the goal of agent-based epidemiological modeling is to estimate the probability distribution of infection states for each agent at next simulation step, which can be defined by the formula below. As one may notice, this formula iterates over the agents and must be computed for each of them. This is the source of the quadratic complexity of the trivial algorithm. We propose two major ways to algorithmically optimize the computation of this distribution. First one is to estimate the contagiousness of each place. In essence, contagiousness is the measure of how likely an agent becomes infected in this place. In this case, the simulation algorithm has two steps. First, iterate through infectious agents and, based on their location, update contagiousness of each place. Second, iterate through susceptible agents and, based on their location, update their infection state distribution. In general, this algorithm has linear complexity, but not suitable for any infection transmission function. This function must not depend on donor's infection state, or, more general, it must be decomposed into two functions which obey the following constraint. Second way to optimize simulation algorithm is to use the procedure we call grouping. Essentially, grouping is tracking which agents are located at each place and time-step combination. After that, we can iterate pairs of agents only inside the same group. This algorithm has linear complexity under the assumption that number of agents is proportional to number of places. This assumption arises from the idea that by increasing the model size, number of agents in each contact group stays approximately constant. One major benefit of this approach is that it is suitable for any infection transmission function. The grouping approach is not straightforward to implement. It requires a special data structure which maps places to a set of agents. This data structure, called multimap, can be implemented in several ways, as a vector of vectors, as a vector of linked lists, and as a hash table. Each approach was tested, and even though we thought that vector of linked list would be the most performant one, as lists are designed to be fast during iteration procedure, the best one turns out to be a vector of vectors. It seems that CPU caching makes major contribution to its performance. Another optimization that we came up with is based on the following idea. Computing the infection state probability distribution requires a lot of multiplications. What if we replace them by summations, which require a lot less CPU cycles to perform? But the only problem, we also need to compute logarithms of each term, which is expensive computation. So, natural idea is to use this approach only for static infection transmission functions, which means that these functions are not dependent on donor, not on recipient states. The effect of this optimization was tested, and on the graph you see the performance increase of it for a variety of model and contact group sizes. As it turns out, this approach is beneficial for small models with less than 10,000 agents. So, the most appropriate decision is to use it for these kinds of models. All of the approaches that we discussed were implemented in the compiler of our modeling language for agent-based epidemiological modeling called CTrace. You can refer to it following the reference in our paper. To test their performance, test model was developed using CTrace and compared to existing approaches. Even though it doesn't capture all the details of each model, it has common general design. To unify the results, we developed a metric which decouples the effect of number of simulation steps, time steps, model sizes, and number of CPU workers running the simulation on execution time. You can see its definition here. In essence, it says the amount of seconds to compute single simulation step for one time step of a model with 1 million agents using single CPU core. On this slide, you can see the performance of our approach in comparison with existing ones. You can find that our approach is at least as performant as the other ones. Unfortunately, we can't decouple the effect of hardware used in our experiments, so we measured execution time in our model on both modern and 13 years old laptop CPU. To conclude, the challenges encountered in the implementation of agent-based model of infectious disease are discussed, with the focus on the time complexity of the simulation algorithm, which is defined as a key issue. A mathematical framework for agent-based epidemiological model is developed. Several simulation algorithms with linear time complexity and optimization approaches are proposed. These proposed algorithms are tested and compared with existing models, and the results demonstrate that the proposed approach is at least as effective as other implementations. Thank you very much for your attention.